So chapter number 2, states of matter. We know matter is anything that is composed of mass or composed of particles and that they occupy space. Now, we define different states of matter, although there are many, but we define the most fundamental ones, solid, liquid, and gas. There are more states of matter as well, but at this stage, we just stick with these three, all right? So moving on, this is the key definition towards matter. Remember, we're not going to go in detail for matter, and the definition of matter is something that haven't been a part of past papers. So let's just stick to what we have and what can come as a part of past papers. All right. So the next thing we have is the simple differentiation table for the between the three physical states of matter, solid, liquid, and gas. Now we do understand that solids and liquids have fixed volume, and that volume can always be measured by putting them in containers or simply measuring them. You know, you can measure the volume of a solid by simple mathematical formulae. I hope you're familiar with a few like length into breadth into height. Are you?
Yes, sir.
And we can simply put a liquid into a container. If the container is graduated, if it has marks on it, we can easily measure up the volume of a liquid. However, for gas, there is no fixed volume because it tries to expand to fill the container, or since it's just the start of the book, so they are writing it in somewhat easier form. So it's better that if you write that it expands to occupy all available space, right? So it's not just about one small container that we can talk about all the time. If you're going to talk about rooms, halls, or even bigger areas, the gases would try to expand to fill them up too. So they try to occupy all available space, any space that they get, right? The simplest of examples is that when we cook food, and we Asians are pretty good with spices. So when we cook food, our food has a pretty good flavor. Apart from that, it has a very good aroma. Usually the food or the biryani is being cooked in the kitchen, but the whole house knows today is the biryani day, right? And I
Yes,
hope you like
sir.
it too.
Mhm.
Okay, so moving on. Density is high for solids. It's moderate to high for liquids. For example, some liquids have less density. We can quote alcohols, we can quote water for this purpose. But when we talk about high density, we can easily quote honey. We're going to later relate it to fluidity as well. We will relate it, this density part, to fluidity part. I hope you understand that density itself comes from physics, and we define density as a formula of mass over volume. How much mass something has and how much area or volume does it cover? Not exactly area, but volume, right? And gases have low density. I hope you understand that this is related to particle model of matter, and gases have low density because they have so many available spaces in them, right?
Yes, sir.
Okay, so solid has a definite shape, and we have a lot of shapes in mathematics. Talking about geometry, you know, the circles, the squares, the rectangles, the parallelograms, the list goes on. We have so many shapes that we have studied in mathematics. We are going to study a lot more shapes in chemistry too. Now, liquid has no definite shape and it takes the shape of the container. So does the gas. It has no definite shape and it takes the shape of a container. Whatever container it is contained in, it would take the shape of that. For gases, even if it is contained in a room, in a balloon, in a cylinder, in something else, it would easily take the shape of it. All right. So moving on, fluidity, and we know gases and liquids are commonly called fluids because they can flow. So the solid does not flow, liquids flow easily, and gases flow more easily than liquids, right? Now, this one does not give you a good differentiation, but let me tell you, gases flow easier than the liquids. Now, if I talk about liquids, their density and their fluidity will depend upon one another. I hope you understand. If the density is moderate, and let me talk about water here, it would have a good fluidity. Or instead of writing good fluidity, we can simply write flow easily, right? And if I quote the other kind of example with high density, right? And I quote the example of honey, you would understand that it flows with difficulty. If
G,
you
sir.
glass of water, you turn it upside down, you're gonna turn anything wet in the way of it. And if you have a jar of honey, you're gonna turn it upside down, then you're gonna wait for the lovely honey to come out of it. And it may take a few seconds, sometimes even minutes if the jar is bigger and it's away from the mouth of the jar, and it takes some time to get out. You can keep on saying honey come out, but honey won't come out, right?
Yes, sir.
Okay, good, good. So if you understand this basic easy part, we're going to move on to the changes of physical states, which is actually a more of an important topic when it comes to these pages. So I hope you already know about melting. It's the conversion from solid to liquid phase, and freezing liquid back into solid. This occurs at specific temperatures and actually are important to opposite to one another. So melting point and freezing point are the exact temperature points at which these processes occur respectively. For example, the melting and freezing point of pure water takes place at 0 degrees centigrade. I hope you're familiar with that. For most of the substances on the planet, the melting and freezing points are same. For most of the substances, please do keep that in mind. There are substances for which the melting point is not equal to the boiling point. Oh, sorry, freezing point. All right. For example, I can quote an example of agar-agar jelly. The melting and the freezing point is not the same. For water, the melting and freezing point is same. For pure water, it's 0 degrees centigrade. The ice melts into water at 0 degrees centigrade, and the water can be frozen back into ice at 0 degrees centigrade. But it's not same for a few of the substances on the planet. So you cannot use the word all the substances have melting points equal to freezing points. Remember to not use that phrase. You may write it down if you want to. Take your time. I
Okay,
would
sir.
suggest you should have the book and a pencil ready in hand today, since I'm going to go quickly through the material and I'm going to ask you to write a lot of stuff on the book. So do you have it ready? If not, take your time, be ready. When you're ready, let me know.
Yes, sir. I've written it.
So are you done writing this one?
Yes, sir.
Good. Let's move on. Let me clear it up. Okay. The next one on the list is sublimation. For sublimation, there are a few solids which convert from solid directly into gaseous state without going into the liquid phase. We call them we call the process sublimation, and for the solid, the verb sublimes. Now, this also happens at a particular temperature. We can give a few examples. We can give the example of carbon dioxide, which in solid form is known as dry ice, because it looks like ice, but it's not wet. The only part is that it's dry. So the first example is carbon dioxide. The second example is iodine over here, which can sublime. So the second example is iodine. Let me tell you, there are a total of 4 examples in your book. The next one would be ammonium chloride. Make sure you write out examples, since the examples are present in different parts of the book. And the formula for ammonium chloride is NH4Cl. And the last one on the list is naphthalene. All right. So these are the 4 examples for the substances that sublime instead of melting or boiling. So the example of carbon dioxide is given over here with the solid name dry ice. The example of iodine is given over here. Are you done writing?
Yes, sir.
Okay, so I'm going to clear it up and I'm going to show you the examples in different parts of the book. This is the example for the figure of iodine. Iodine sublimes. Whenever we heat it up, the solid directly converts into gas. So you would notice that there is this dark black solid over here, and it is directly being converted into gas, which is dark purple in color. So you'd notice a gray black solid and purple vapors. You won't notice any liquid in there. Since for most of the substances, they convert from solid to liquid and then from liquid to gaseous phase, iodine does not, it sublimes. Now moving on, if I go a few pages forward, you would notice that we do have an example of, for sublimation. Take a look over here. Sublimation, and you'd notice for the example of sublimation, they have used ammonium chloride over here as a part of separation technique. So now you know that there are more than two examples that they're just given on the first page of chapter 2, carbon dioxide and iodine. Apart from those two, we have ammonium chloride over here. And we're going to discuss the example of naphthalene a little later in the book. That's why those four names. And they may come up with any new substance and they may tell you the fact already. You cannot memorize all the examples, so don't worry. These are just the four that you need to keep in mind. Make sense?
Yes, sir.
Good, good. Let's move on. Let's get to this big diagram, which actually clarifies all of the processes for us in just one single diagram. So discussing the changes of physical state and the effect of increasing or decreasing temperature at atmospheric pressure. Now, these terms are sometimes not understandable by the student, or sometimes the teacher do not go through with these terms at the very start of the book. But when you're about to appear for your exams, you should be very much familiar with what they mean. So we're going to change the physical state, and we're going to do that by increasing or decreasing temperature, but we're going to do that at constant or atmospheric pressure. We're not going to change the pressure while we're going to change the temperature. So that's how we go with these processes. So while freezing or melting or subliming or evaporating or condensation or any other processes, we're just going to increase or decrease the temperature. We're not going to change pressure. That's what this line means. So keep that in mind. Fair enough?
Yes, sir.
For the rest of the definition, it's pretty easy that you already know. You do understand that solid goes into liquid by the process of melting, and this occurs at a specific temperature, so it's known as melting point. The liquid actually vaporizes or goes with the process of vaporization. Vaporization is also known as boiling. Okay, so the liquid converts into gas at this specific temperature. Boiling occurs at a specific point. We call that boiling point. We're going to define that a little later in the same page,
Okay, sir.
right? So vaporization or boiling is almost the same thing. However, evaporation is something different. Right after this definition, actually this diagram, I'm going to start with evaporation. So there is a difference between boiling and evaporation. We're going to clear out the difference as soon as we're done with this diagram. So the gas can be converted back into liquid. The process is either known as liquefaction, which is actually was discussed back in chapter number 1. We discussed the liquefaction, we discussed the fractional distillation of liquid air, and liquefaction is actually the process by which we cool something down to convert a gas into a liquid. Now, liquefaction and condensation are two separate things, just like evaporation and boiling were. Liquefaction occurs at a specific temperature, like boiling does. Condensation and evaporation may occur at different temperatures. So I'm going to discuss that a little later, don't worry. And then liquid can be converted into a solid by freezing or solidification process. Yeah, these two might be a little different, but at this point, freezing and solidification will mean the same thing, conversion of solid into liquid phase. So
Okay, sir.
melting and freezing occurs sharply at the same temperature for most of the substances. Boiling also occurs at a specific temperature. However, evaporation and condensation occurs at a range of temperatures. Sublimation is something different. Few solids change from solid to gas upon heating or vice versa, right? So gas to solid upon cooling. They don't usually tend to go to liquid phase. I hope you're clear with the whole diagram, right?
Yes, sir.
Good. Moving on. So we can convert a solid specifically at melting point into a liquid, or liquid specifically at boiling point into a gas. And by decreasing temperature, we can go with the reverse process, which means these processes can be easily reversed. Now, let's explain evaporation, boiling, condensation, steps like those. Let's start with evaporation first. Evaporation is a process in which liquid changes into gas, and to define this process in specific, that always takes place at a temperature less than boiling point. So if pure water is converted into vapors at exactly 100 degrees centigrade, this would be known as boiling, since that temperature is boiling point, since 100 degrees centigrade is the boiling point of water. But if pure water or any kind of water, let's say, is converted into vapors, and that occurs at a temperature less than 100 degrees centigrade or 99 degrees centigrade. Let's write 100. That's not right 99 because this might confuse you. 100 degrees centigrade, that is evaporation. So water converting into vapors at 99 or 90 or 80 or 75 or 50 or 40 or 25, any temperatures like those would be evaporation. So boiling occurs at specifically boiling point, and any temperature lower than boiling point, if a liquid converts into gas, if a liquid converted into vapors, it would be considered as evaporation. Do you understand the difference?
Yes, sir.
So boiling only occurs at boiling point. Keep that in mind. Now, evaporation actually takes place from the surface of a liquid. All right. What is evaporation? Evaporation, the concept of evaporation is pretty simple. You have a big utensil, and that utensil is filled up with water. The molecules at the surface may be able to leave the surface. We call it a vapor. And we call this process as evaporation. Since any molecule from the surface of the liquid may leave the surface and get to the nearby atmosphere, we call it evaporation. Easy enough?
Yes, sir.
Good, good. So evaporation is actually affected by different factors. Some of them are discussed over here. Some of them are discussed in other parts of the book. So let's write all the factors that are going to be implied by this book. Now, the larger the surface area, the faster the liquid evaporates. So of course, surface area matters. So the first factor is surface area. And it's pretty simple. When you wash your clothes and you want to dry them, what do? You don't juggle them up into a ball and throw them somewhere. Instead, you try to spread them as much as you can so that they are easily dried up. Make sense?
Yes, sir.
So larger the surface area, easier it would be to evaporate it. And smaller the surface area, slower will be the rate of evaporation. The second thing, warmer the liquid, the faster it evaporates. So of course, the second directly proportional factor would be temperature. Higher the temperature, faster would be the rate of evaporation. Lower the temperature, slower will be the rate of evaporation, right? Because on sunny days, on hot days, we can see the puddles dry up, or the water gets dried up, or our wet clothes gets dried up pretty quickly. Even that happens to our perspiration, right? But on, let's say, on a cold day, that doesn't occur at the same rate. Of course, it's going to be slower. But there are some other factors apart from the ones that are quoted over here. Can you come up with another factor apart from these two?
Um,
Okay, take a look at this one, and can you relate this factor to the rate of evaporation? Wind speed. On windy days, if we have a strong burst of air going through the atmosphere, the city, you would see that the clothes dry up quickly. But on normal days, when we don't have a specific airspeed, the same thing won't happen. Same is the way when you have worked out a lot and you have perspirated a lot, you tend to come in front of a fan. How? The faster airspeed from the fan would try to increase the rate of evaporation, and you'll dry yourself up a little bit faster than usual, right?
yes,
Understandable?
sir.
Good,
Mm,
good. So number 4, nature of a liquid. Some liquids dry up faster than the others. Petrol. If I fill up a glass of petrol and I put it somewhere, and at the same time I fill up with at the same height a glass of water and I put it somewhere, if I come back the next day, the glass of water would be there with a little bit of evaporation. But if I come back at after 20 minutes, there would be no petrol in that glass. Not because it's stolen by someone, it's because it evaporates too fast, right?
Yes, sir.
Okay, good, good. So the nature of the liquid is something that we can note. Okay, number 5 and last, humidity. Familiar with this word already?
Yes, sir.
So it's the amount of moisture or water vapor present in an environment, and it actually differs from area to area. Some areas are more humid, the ones that have more rain, that receive more rainfall during the year, they are usually more humid than the ones that are usually dry. So actually right now you're living in an arid, dry climate, so you don't have enough of humidity. But if we talk about a place that receives more rainfall than you, of course the area is going to be more humid than as compared to yours. And
Yes, sir.
humidity is something that usually comes in the form of percentage along with the different weather news that we get every day. We are in a practice of looking up the weather patterns, and we actually plan our daily routines according to that. Maybe not you, because you tend to have the same weather for the most of the months of the year, but not every place on the planet behaves in the same way, right?
Yes, sir.
Not bad mouthing about Saudi Arabia, but the climate tends to remain the same for most months of the year. I hope you
Yes.
understand that too, right? Okay, good, good. So these are some factors that can affect the rate of evaporation, the speed of evaporation, how fast or how slow a liquid is going to evaporate. So if we're good with evaporation, can we move on?
Yes, sir.
Good. So moving on, let's see the next page. Now, if the liquid tends to be converted into a gas at a specific point, the temperature point is known as boiling point. The process is known as boiling. It occurs at a specific temperature. The boiling or the boiling point can be defined a little bit differently. We really consider the definition of boiling from liquid to gaseous phase a childish definition for this process or for this temperature point. So let's define it a little bit differently, which the book is going to do right after this pink portion. So let's go through with the pink portion first. Water evaporates fairly easily and have a relatively low boiling point. If a liquid has a low boiling point and it evaporates easily, we have a name for it: volatile liquid. Volatility is a property that can be compared for two different liquids. Ethanol has a boiling point of 78, water has a boiling point of 100. We can easily say ethanol is more volatile liquid than water, which means having a lower boiling point, ethanol would be able to evaporate faster and easier than water. Make sense?
Yes, sir.
Now, the reverse of evaporation is condensation. This is usually brought about by cooling. In this case, the gas is converted into a liquid state, and this can happen with a lower temperature. But let's explain boiling point. Let's define boiling point separately. I need some white area for that. Okay, let's see, where can we do it? Okay, let's do it over here. Now, before I define boiling, there are a few things that I need to explain to you first. Now, I hope you are familiar with the word pressure from physics, and you have defined pressure as force over area in physics, right?
Yes, sir.
If I talk about gas particle being contained in a container, you know that the gas particles keep on moving randomly throughout the container. I hope you already know that the gas particles may collide with one another and may collide with the wall of the container as well. Now, If a gas particle collides with wall of the container, it's going to collide at a specific area, right? And it's going to collide with a specific force. Now, that force over that area is the pressure exerted by that specific molecule. Now, if we're talking about a few molecules that are colliding at different points on a container, the overall force over area would be the overall pressure of that gas particles inserted by those particles, right? Make sense?
Sir, can you please repeat this again?
The overall force of all the particles contained in a specific area, that overall force and that overall area will be considered as pressure of the particles inserted by the particles in a specific container, right?
Okay, sir.
Means we're considering pressure as an overall term, not just for one specific particle. We're considering it for an entire container because the container will consist millions of particles colliding almost all the time at different points of the walls of the container. So considering an overall impression for the overall force over overall area would be the pressure of that specific gas enclosed in the container, right?
Yes,
That's
sir.
the concept of pressure we have taken from physics. If I try to apply the same concept for the boiling process, let's explain it a little bit. Now, let's consider a container which I fill half up with water. Let's say the liquid is water. And I hope you understand that if I start heating it up, the water will slowly gain the temperature. It would gain from the heat, the particles would gain some kinetic energy, and some of the particles would tend to leave the surface and would be converted into vapors, right? We say that the water is being converted into gas. If I keep the flame on, there would come a point that there would be vigorous bubbling, and I'll call that point as the boiling of that specific liquid, right? This is something that you have defined in the similar way. Now,
Yes,
what
sir.
if I don't talk about an open container anymore? What if I talk about a closed container? In a closed container, the particles will not be able to leave the container. What would happen is that some of the particles will leave the surface of the liquid, and some of the particles may also come back, right? So evaporation and condensation will occur at the same time. But that's not what we are concerned with over here. I hope you understand if there are some particles forming, there are some vapors forming, those vapors will be able to collide the wall of the container in the similar way that we have described over here. And
Yes,
let me
sir.
change color in a specific area and a specific force. And this would happen throughout the container and on the surface of the liquid as well. So when this happens, this is normal pressure. This is what we call pressure. Since this specific pressure is exerted by vapors, we call it vapor pressure. Make sense?
Yes, sir.
Now, outside this container, there would be some air, and there would be particles of gas in the air. As you already know, the air is filled with nitrogen, oxygen, and different many other gases. And those particles may also collide at the same area, putting some pressure over it, right? For this specific pressure, we call it atmospheric pressure, the pressure created by the particles present in atmosphere all the time. Air pressure, we also call it. But atmospheric pressure is a much better term to describe it. That is present throughout the atmosphere of the planet because the atmosphere is filled up with air, and air is actually a mixture of different gases like nitrogen, oxygen, so on and so forth. So
Ji, sir.
what has boiling point to do with all of this? Let me explain. A temperature point at which vapor pressure becomes equal to atmospheric pressure That specific temperature point is known as boiling point of that liquid. Make sense? When there are
Yes, sir.
enough vapors, when we have heated this liquid good enough to have so many vapors, as many particles as there are outside, and those particles are creating atmospheric pressure, and the particles inside are creating vapor pressure. When both these pressure becomes equal, that temperature point is known as boiling point of that liquid.
Yes, sir.
Now, you must think we have so easy definitions for melting point, freezing point, evaporation, condensation, sublimation. But when it comes to boiling, we have such a difficult definition. And instead of relating the definition to the states of matter from the conversion of liquid state to the conversion of gaseous state, instead we are talking about pressure all the way. Why? A question arises, why have we been talking about pressure all the time? We have been talking about pressure all the time because for the planet Earth, the pressure is maintained at ocean level. Since ocean level is maintained by the water and there is more water on the planet than there is land, so at ocean level the pressure is known as atmospheric pressure, right? And this pressure changes its value when we go at altitude. For example, if we talk about mountains, and mountains actually have a higher altitude, the pressure decreases, the atmospheric pressure decreases. So what happens? At higher altitude, if there is less atmospheric pressure, will require less vapor pressure, will require less temperature. So actually the boiling point of liquids decrease at a higher altitude.
Yes, sir.
Funny, right? Now let me clarify that with some few examples. Were you writing? Sorry, I cleared it up.
Yes, sir, I'm done.
You done writing? Okay, good, good. So I'm gonna clear it up and let's move to the next page so I can explain. So the boiling point of pure water is equal to 100 degrees centigrade, and that's at atmospheric pressure. All right. Let's talk about higher altitudes. Name a mountainous area that you like, that you'd love to visit. Name one.
Um, Two.
Do you know the hike is not easy? It's one of the most difficult heights of the world. Well, let's talk about K2. It's the second highest peak. If we talk about Mount Everest, it's the highest peak on the planet. I hope you're familiar with the names, right? Let me tell
Yes.
you that the boiling point of water at Mount Everest is 69 degrees centigrade and not 100, because at that high altitude, the atmospheric pressure falls, so the boiling point also falls. And it's written in these lines, last lines of the previous paragraph and the starting lines of this paragraph. On a high mountain, it is lower than 100 degrees centigrade. The value around at the peak of Mount Everest, and this is actually the peak, not the base of Mount Everest, it's around 69 degrees centigrade. For K2, it's a little higher than 69, but it's definitely much lower than 100. That's why
Yes, sir.
we needed to relate the definition of boiling point with atmospheric pressure, since the boiling point changes with the altitude, which means if we talk about ocean and if we go into the depth of the ocean, the boiling point would increase from 100. And yes, it does. After every 1 meter of the ocean's depth, the boiling point increases.
Okay,
Now,
sir.
look at God's work, look at Allah's work. Since the higher mountain, we have colder temperatures. So he asks us to go for a little bit of heat, and even the water would boil easily at those temperatures. If we were supposed to heat it up to 100 degrees centigrade, this would have been a bigger problem. It already is a bigger problem to boil water at the peak of Mount Everest, even at 69 degrees centigrade. But for 100 degrees centigrade, it have been a much greater problem. I hope you can understand what I'm trying to say.
Yes, sir.
Good, good. So if the surrounding pressure is increased, and that we can do artificially, right? And we do it in a pressure cooker. I hope you're familiar with the name. It's being used in
Yes.
the kitchen.
Yeah.
Usually it's a little bit scary for the kids, but moms or maids use it with much of the ease. Now, what we do in a pressure cooker is that it's a big container on which we have actually a heavy lid, and that lid is covered with other smaller lids or portions or heavier portions. What we do is that we increase the boiling point of the water around 120 degrees centigrade by increasing the pressure by putting on a heavy lid on the system, and the food cooks more quickly. When it comes to food, meat takes too much time to be cooked in a simple way, and pressure cooker takes a lot less time. Meat actually requires from 4 to 8 hours to be cooked at normal pressure. In a pressure cooker, we can cook it in 30 to 40 minutes. So instead of hours, good invention. Same goes with lentils. I don't know whether you like lentils or not, Tale. Actually, this is something a lot of the memes in Indo-Pak subcontinent region are there about different kinds of lentils. कुछ बच्चों को दालें पसंद होती हैं, कुछ को बुरी लगती हैं. Which category do you fall into?
I like them.
You like them or you dislike them? I wasn't able to hear you out.
I like them.
Good, good. Okay, so I'm also in the favor of them. I really like them. Okay, so I hope you understand this point. And if they talk about a mountainous region, you will never know what exact the boiling point of water would be. So how are you going to answer the question like this? At a mountainous region, less than 100. Do not try to go with an exact value. You might not be correct with it. Okay?
Yes, sir.
So that's the way to answer it. And for the depth of the ocean, that's the way to answer the question.
Yes, sir. Okay.
So now you know how to link these values and how to answer these questions. You also understand the definition of atmospheric pressure or standard pressure, which is taken at sea level or ocean level. Good enough?
Yes. Yes,
Now,
sir.
a couple of more points before we wind up the class. A pure substance consists of only one substance. Okay, so if you mix any substance with any other substance, it's not pure anymore. So water is pure if there is only water. If you add anything to it, it's not pure. Add salt to water, impure. Add sugar to water, impure. Mineral water, which is actually minerals dissolved in water or salts dissolved in water, is an impure form of water. Make sense?
Yes, sir.
So most of the things that you handle with in daily life are actually good mixtures. They're impure. But if the impurity is good for you, we do not call it a contamination. Contamination is an impurity which is not good for you. Now, if we talk about pure substances, they melt and boil at definite temperatures. That's the best part. For any pure substance, there would be a specific temperature at which it is going to melt or it is going to boil. We have a lot of examples in this table. Right? Oxygen, nitrogen, there are gases, there are liquids, there are solids. And we also have one example to sublimation. This one sublimes carbon dioxide at the bottom of the table. So I hope you do understand at negative 78 degrees centigrade, this gas can be converted directly into solid, or the solid can be converted any temperature higher than negative 78 back into the gas. Now, We can easily test or check the melting and boiling points. We usually do it with digital apparatus. Digital apparatus is something very good. It gives us really accurate values for melting point, or you can go for a manual way of checking the melting or boiling point of anything you'd like to, maybe a solid, maybe a liquid. We usually use a water bath for this purpose. For anything below 100 degrees centigrade, if it melts or boils it below 100 degrees centigrade. For anything who has a melting point or boiling point above 100 degrees centigrade, we use an oil bath for that purpose. All right, so that's the manual way of checking it. This is a digital way of checking it. Remember, the manual ways are not as accurate as the digital ways, because you might make a mistake. You might be actually not having complete attention to the experiment, and you might be into talking into your friend and miss out, or not being vigilant and make out a human error easily while going with this kind of manual experiment. Most of the time, what I see with students is that they fall into horseplay. They try to tease their friends, they try to talk to their friends, and they're not vigilant enough for the experiment. And for this kind of experiments, when we are manually trying to find the melting or the boiling point, if you're not vigilant enough, you won't be able to observe the bubbles that have started for during boiling, or the change in level if a solid is being melted into a liquid. And if you're not vigilant enough, you're definitely going to miss that point. All right.
Jesus.
Okay. This table seems like a nice and easy table. You do not need to memorize any values out of this table except for this one, for pure water, which you probably already do. So what is this table about? This table is about a very important kind of questions, and let me clarify. Usually what happens is that this part is a part of the question, this is a part of the question, this is a part of question, this is a part of question. This is something that they usually ask as an answer. So they tell you what the substance is, they give you its melting point, they give you its boiling point, both in degrees centigrades, and then they give you a specific temperature at which you need to find its physical state. So the formula is really easy, and I tend to ask my students to write the formula. All right. Now, if the given temperature is the temperature that is quoted in the question. In this table, the given temperature is continuously 20 degrees centigrade. So if the given temperature is greater than the boiling point, then the substance is a solid. Now, if the given temperature is less than the melting point, the substance is, wait a second, my bad. I have made a mistake even at the start. No, but it's not a solid, it's actually a gas. And this one is a solid. And if the given temperature is smaller than the boiling point, but is greater than the melting point, then this is a liquid. That's how you're going to know whether any specific substance would be a liquid, a gas, or a solid at any given or any specific temperatures. And you can apply the same rule to this whole table, right?
Yes, sir.
Take a look. Sulfur has a melting point of 115, a boiling point of 444. The given temperature was 20 degrees centigrade at the top of this table, hence it's a solid. Why? Because the given temperature is smaller than both melting and boiling points. If the given temperature is both bigger than melting and boiling points, it's a gas. If the given temperature is greater than the melting point, but it's smaller than the boiling point, it's a liquid. Make sense?
Jesus.
Now, the given temperature does not necessarily have to be 20 degrees centigrade. They might give you the given temperature at 100, at 1000 degrees centigrade, at minus 100 degrees centigrade. And usually all of these values are easy until unless they come up with something in negatives. Now, I'm going to ask you a question from the same table. Now, move on to the second row of the table. We're talking about nitrogen, and the given temperature is minus 200 degrees centigrade. Now, what would be the state of nitrogen at minus 200 degrees centigrade? I hope you're done writing with the rules that I wrote at the bottom, which I just cleared up. Okay, then take a look at the rules and then try to answer your question. It's not cheating. It's a test of understanding.
It will be solid.
Sorry?
It will be solid.
No, minus 200 is actually a bigger temperature than minus 210, but a smaller than minus 196. So it's actually right in between these two. And if it's right in between these two, it must be a liquid at this temperature. Remember, in negatives, a bigger number becomes smaller and a smaller number becomes bigger. Don't forget the number line from mathematics. Actually, that's not a part of chemistry, that's a part of mathematics, that on a number line, a number is greater than a number if these are positive. But if I talk about the vice versa, then minus 100 is actually a greater than number than minus 200, which means minus 200 falls right in between minus 210 and minus 196. Minus 200 is actually a bigger number than minus 210, so it's greater than the melting point. It's smaller than the boiling point because minus 196 is actually a bigger number than minus 200. So if the given temperature is in between the melting and the boiling point, the substance is said to be in liquid state. So I've seen students do it really well with positive numbers, but when it comes to negatives, they can't really actually are able to handle negatives. And if that happens, you don't have a problem with chemistry. You have a problem with the basic concept of number line from mathematics, probably from class 5 or class 6, not even from this class. All right. So make sure you're good with maths. If you're good with maths, the mathematical parts in chemistry are going to come easy to you. If you're not good with maths, the mathematical portions in chemistry or physics or biology are going to come really difficult to you. I don't know how good you are with maths. How good are you with maths? If you have to rate yourself out of 10, how would you rate yourself?
5.
Oh my God. Then you need to work at maths much more than you need to work at with chemistry. Since maths is going to be a part of chemistry, it's going to be a part of biology, it's going to be a great part of physics. So be prepared for it. The better you're going to go get with maths, the better you're going to be with all these subjects, specifically the mathematical portions of these subjects. Now, I'm going to